All right. Now, I had this video that I called The True Connection Between Sound and Light. And I got a couple of dislikes on that video. So, what I'm going to do is I'm going to make this part two of that video so that you can specifically understand where science is wrong and how to be more precise in your measurement. All right. So, we're going to fix the measurement issue. All right. Now, scientists don't agree on what to call the wavelength of specific color ranges. Alright? But they know that red starts at the beginning because they have their 7 color system, Roy G. Biv, where red is at the bottom and violet is at the top. Well, of course, but red isn't really at the bottom because there's a color below that. And violet isn't at the top because purple is above that. So you have raspberry at the bottom and purple at the top. So there's a difference between a purple and a violet. Alright? There's difference between raspberry and red. Now that's just dividing the visual octave into 12 parts. Now we know that there's at least 12 colors that you can conceptualize. So you have your 3 primaries, your 3 secondaries, and your 6 tertiaries. That equals 12 different colors. That's basic color theory. Now they just don't know where the terahertz range starts for all these different colors because they don't know where red starts, and that's their issue. So you can go into Google search and type in the frequency range of red colored light. All right? And you're going to get different sources that give you different ranges. So who's right? Well, the wavelength in between all those different ranges, you'll find your red color, sure. But why not be more specific in your measurement? All right, so some sources will say that red starts at 400 terahertz. Others say it starts at 405 terahertz. And others say it starts at 430 terahertz. Okay, so which one of these guys that came up with these numbers, which one is right? Well, it could be more refined. So when you lower the frequency by 40 octaves, 40 octaves, 40 octaves lower than 400 terahertz will give you 363 hertz. And that sounds like this. So that's your F sharp. That's in the F sharp range. If you have absolute pitch, you hear that, you know it's F sharp. So that's one note. So is F sharp a red? What about 405 terahertz? Now 405 terahertz is 40 octaves higher than 368 hertz, which sounds like this. Okay, so if you have your absolute pitch, it sounds like the same range of note. It's still an F sharp. So, okay, so F sharp must be red. David Lucas Burge must have been right. Well, what about 430 terahertz? 430 terahertz is 40 octaves higher than 391 hertz. And that sounds like this. So it's in the G range. So, but this is at the bottom of the range, okay? This is where the frequency range starts. So if it starts around F sharp G, then it should end around A sharp. But that's spanning in between many different divisions of colors. So if it can't be an F sharp, red can't be an F sharp, because red can't be both F sharp and G. So it's wrong. There's a reason why he only had a couple of colors that he labeled. All right? Just because the ranges were so vague. Now, if there's 12 hours on a clock and sound is measured in time, so there's 12 notes in music and there's 12 colors that you that you can conceptualize, your 3 primaries, 3 secondaries, and 6 tertiaries, then you can connect the TSL matrix, the time, sound, and light, so that it's more precise in the measurement on an energetic level. All right, so I say that red starts at around 448 terahertz. Now that's still within the range, because people will say that red starts at 405 and ends at around 480. So my number is in that range, but it's just more precise. Now, 40 octaves lower than 448 terahertz will give you 407 hertz. Now, 407 hertz sounds like this. So it's in between the range that they give. So red, a pure color is in between the range that they give you. So red must be an A flat. All right. Now, that's just starting your red, all right? But 448 terahertz is higher than where they're saying red starts. They say that red starts at raspberry. Now, raspberry is around 423 terahertz. So it's still within that range. You can look out and see a raspberry color, and you could confuse it for the wavelength of red, but there's a difference between raspberry and red. Now you have 12 different colors. So you have raspberry, red, orange, yellow, lime, green, turquoise, cyan, blue, violet, purple, and magenta. So those are your 12 different colors, all right? Magenta isn't really on the scale. They say that it doesn't have a specific frequency range. But numerically, 400 terahertz and 800 terahertz is within that spectrum. It's on the scale. They can tell you that you can't see the color pink, but if you have any wit in your mind, then you know that you can see the color pink. So it has to have a visual color frequency. All right? So you have magenta at 400 and 800 terahertz. So it's like there's two different magentas. They have the same chroma because the octave completes. 800 divided by 2 is 400. So you can say that the range of visual color is around 405 terahertz to 790 terahertz. But the thing is, to extend the range of what you say you can see, some of those people only see 7 colors, and they confuse the ranges in between. So extending the numbers in either direction isn't going to change what's in between. Now, so you have raspberry, that's half red and half magenta. So it's like a dark pinkish red, all right? Now that's at 423 terahertz. Now 423 terahertz will sound like this. It's your G. So the scientists were confusing raspberry and red. And then red is 448 terahertz. That's an A flat. 40 octaves lower than the terahertz frequency range. That's how I get the audible sound of the color. Because you can play two different notes that have the same color, the same note. They're just in different octaves. But it's the same note. It's the same color. And then you have orange. That's around 475 terahertz. Now that's the 40 octaves lower than that sounds like this. Now that's an A. And yellow is around 503 terahertz. 40 octaves lower than that will give you this. Now that's a B flat. It's in the range of the B flat. It might not be in standard pitch, but there's a range of each note. There's a range of each color. Now this is just making it more precise. Okay, now next comes lime green. So it's like a yellow, half green. Half yellow, half pure green. Now pure green is in between a pure yellow and a pure cyan. So that's what I mean by pure saturated resonances. The pure colors. You got red, green, and blue that they call the wavelength of violet, they call it blue, but it really should be called violet because roses are red and violets are blue, but violet is a dark blue color. So your three primaries, red, green, and violet, or red, green, and blue, the three dark notes, the three dark colors. And then your secondaries, yellow, cyan, and magenta, those are bright, okay? And then your six tertiaries is a mixture between a bright and a dark color. Now, bright and dark isn't to be confused with warm and cool, because you can have a bright cool color or a dark cool color, a bright warm color like yellow, or a dark warm color like red. You see what I'm saying? So don't confuse the stuff. It's very simple. All right. And then you have, lime is at around 533 terahertz. Now these numbers that I'm giving you is within the range of what they say the colors are anyways. I'm just giving you a more precise measurement. All right, so 40 octaves lower than 533 terahertz will give you this sound. Now that's a B. Green is around 565 terahertz. 40 octaves lower than that gives you this. That's a C. It's in the C range. So you have green in the middle of the piano at middle C, just like C is in the middle of the rainbow at green. You see the connection there? So, okay, and then the next division would give you turquoise. Now, this bluish-green range confuses a lot of people. They don't know what to call it, so they just say it's black. All right? But there's different saturations of bluish-green colors. You have blue-green, which is in the green range, and you have green-blue, which is in the blue range. One's teal and one's turquoise. All right? So when I give the color for turquoise, teal is still in that range, all right? It's within a quarter tone. It's not a full half step. So there's still 12 divisions. So turquoise or teal, whatever you want to call it, something that's in between green and cyan, is around 599 terahertz. And that gives you this sound. Now that sounds like a D flat or a C sharp. All right, so that's what that color is. And then you have cyan, okay? Cyan is around 634 terahertz. And that gives you this sound. 40 octaves lower than 634 gives you this sound. Now that's a D. And then you have blue. Now remember, they called the violet wavelength, they called it blue. But blue is brighter than violet. So blue is in between violet and cyan at 672 terahertz. Now 40 octaves lower than that will give you this sound. It gives you an E flat. So he was right about that. E flat is blue. And then you have violet, which is the primary because it's darker than purple and blue. And then that's at around 712 terahertz. 40 octaves lower than that will give you this sound. So that's an E. So you have your three dark primaries giving you your augmented triad, your C, E, and G sharp. All right? It separates the octave into 3 equal parts. That's just when you visualize a color wheel in RGB, that's just where the colors are, okay? Now remember, what they call blue as a primary is actually the wavelength of violet, because violet is a dark blue. And then you have purple, which is not a dark blue, it's not a violet. Purple is in between the pink magenta and violet, the dark blue. So purple is like a pinkish violet, a pinkish blue. Now, that's at the range of 755 terahertz. And 40 octaves lower than that will give you this sound. So that's an F. And then you have the octave completing at 800 terahertz. So magenta is off the scale. They say it doesn't have a specific frequency just because it has two. All right? So you have magenta going back to F sharp. So you have your 12 different colors, your 12 different notes. They're octaves of specific wavelengths. Now, I hope that clarified some things, because disliking a video just because you don't understand or don't agree, just because you would look up the frequency range and pick a certain range that is incorrect to start with, that's going to throw off all your wavelengths. You're not going to know the difference between an orange red, which is a dark orange, it's closer to red. You'll confuse an orange color with red. You won't really know the difference. So we're refining what to call each wavelength. All right. So once again, you have your F sharp at magenta, your G at raspberry, your A flat at red, your A at orange, your B flat at yellow, your B natural at lime, your C at green, your C sharp at turquoise, your D at cyan, your blue at E flat, your E at violet, and your F at purple. And it goes back to F sharp at magenta. Now, when you visualize the quarter tone, you get all these different saturations in between, but these ranges are there. You can divide the octave, the visual octave, into hundreds of different colors, but you still have your 3 primaries, your 3 secondaries, and your 6 tertiaries. All right? All right, so I think I explained that pretty well. Now, if you have questions, ask me, and I'll explain. But I know what I'm talking about.